Hi guys, my name is Ernest and I'd like to welcome each and every one of us to my channel of Ernest Sciences and Mathematics TV channel. And I would kindly like to request new members to subscribe, engage us in the comment section and also ring that notification bells for various updates. Now in my channel I normally discuss various topics for sciences and mathematics and their various application areas. Now in our discussion today I'm going to look at the concept of quantum numbers and shapes of orbitals. And these are going to be solutions of a Schrodinger's equation or a elimination of the two concepts basically that we have discussed concerning the various orbitals and quantum numbers. Now in this case, we are going to look at this aspect of quantum numbers perhaps in an individual form. Now, I mentioned earlier that basically each orbital of various atoms are going to be described by a set of specific quantum numbers. And in this case, I mentioned a number of quantum numbers from our previous discussion. The first one being the principal quantum number, which we had designated using the letter n. And then I mentioned about the angular momentum quantum number, which we had designated using L. And then we had mentioned the concept of magnetic quantum number, which we had given in terms of ML. And there was this last one that we had given, which is the spin quantum number, which I'm going to elaborate in this specific discussion. Of course, we had given this one using an initial S given as such. Now, these various quantum numbers are going to be assisting us in trying to describe, of course, their implication in various orbitals. And as I mentioned from our discussion on the concept of Schrodinger's equation, basically this set of numbers are going to be numbers that are going to describe specific aspects of electrons in an atom, and one of them being the energy position and particularly orientation of these electrons in an atom, which basically we're going to see in details in this specific discussion. In this case, of course, I'm going to limit myself to the discussion on the concept of the principal quantum number. And in our subsequent discussion, we are going to look at each individual set of these specific quantum numbers, perhaps in a detailed form. Now, in this case, of course, I'm going to look at this specific concept of the principal quantum number. And as I said, of course, each of the orbitals of an atom are going to be represented by three quantum number. And of course, an electron in an orbital is going to be represented using a set of four quantum numbers in that specific order. Now, in this case, perhaps I can just give it in a summary form. So we're going to describe an orbital of each atom using the three quantum numbers of the principal quantum number, the angular quantum number, and then we're going to describe it using the magnetic quantum number. And each electron in an atom, of course, as I've said, is going to be represented using four quantum numbers. And these are going to be the principal quantum number, the angular quantum number, angular magnetic quantum number, angular momentum quantum number, and then we shall have the magnetic quantum number. And there's the last one that we are going to look at, of course, which is not going to be a solution that is solved using the Schrodinger's equation, which I mentioned. And of course, this is going to be particularly concerning the orientation of an electron in an orbital, which is, of course, discussed in some of our videos. Now, in this case, the principal quantum number is going to be describing this specific aspect of energy. And of course, it's going to give us various aspects of the distance between the nucleus and an electron and other various forms which we are going to see. Now, I mentioned the concept of course, the wave-particle duality, whereby we have to come up with this specific aspect of an orbital and various aspects of the wave-particle duality, which of course culminated in various aspects, and those are described basically by Niels Bohr and Erwin Schrödinger. Now, in this case, the principal quantum number which I've mentioned was proposed by Niels Bohr. And of course, we are going to see that the works of Niels Bohr are going to play a significant role in trying to develop different aspects of the topics of quantum mechanics. And of course, Niels Bohr's contribution is going to assist us in trying to describe, of course, the characteristics of various, of course, subatomic particles, which we mentioned for electrons protons and other small particles which are going to be of that nature. Now we had mentioned, of course, that apart from it describing the distance between the electron and the nucleus, it's also going to describe energy which we can give in terms of perhaps this specific description, whereby we are going to denote distance using this specific representation, which is going to be the ratio between this value of the square of the value of n over z. And of course, we had solved this one for a hydrogen-like species in one of our videos, which I'm going to put a link in our description box. And this was equivalent to 0.529 angstroms given as such. And this denoted the distance between the nucleus and, of course, an electron in a hydrogen-like species. Now, in that particular aspect, of course, we had also used the aspect of energy and tried to describe this one. And of course, this was a negative value given as such. And this was, of course, I might call this. We are going to have energy described in forms of joules, and of course, we can have this one given in terms of. I'm just going to give this particular figure. Perhaps you can check so that we are going to be at bar with this. So this is going to be 313.3 kilocalories per mole, and this is going to be equivalent to the energy of this specific electron in an orbit where this specific electron is present. Now, of course, we're going to see that we had come up with a specific formula to describe the maximum number of electrons in an orbit, and that's going to be represented by this specific quantum number that we've given for n, given as the square over n times 2 given as such. And therefore, that's going to provide for us, the principal quantum number is going to provide for us additional information concerning the maximum number of electrons, apart from it describing the concept of energy and the distance, which we have, of course, listed on the board. And of course, it's going to give us some of the information about the various shells which we have mentioned for K, L, M, N, etc. Remember, we had mentioned that for us to describe the position of an electron, there are various levels which we had discussed. Now, I mentioned the concept of energy level, the subshell, and then I talked about the orbitals. Now, in this case, we're going to look at the concept of shells, which are basically going to be orbits described by these specific letters, which are given our notation for K, L, and M. Now, the principal quantum number is going to give us information on various aspects of these specific orbits, which are going to be found within the space of an atom being described by various orbitals, which we have seen, of course, for SPD and F from our previous discussion. Now, in this case, it's also going to describe the characteristic of the energies which we have, the energy which we have mentioned, and of course, we are going to see that apart from it being important for us in describing distance energy, the maximum number of electrons which can be found in this specific orbit, we're going to see that this principal quantum number is going to generate for us a formula for describing angular momentum quantum number, which I've mentioned, and of course it's going to form for us a basis for describing that. Now, in our description of a one-dimension box, or of course a particle in a box, I've mentioned that we can describe the angular momentum using this specific formula, whereby I say that this can be described in terms of of course, a product of n times h over 2 pi, and that, of course, is going to be a derivation of this specific notation that we have given for that quantum number, given in terms of the principal quantum number given as n. Therefore, that's going to assist us in trying to calculate the principal quantum number, or we can find a derivation of the angular quantum number using this principal quantum number as one of the ways of trying to find, of course, the angular momentum, which is another quantum number which we have described from my initial description, or of the various range of quantum numbers which are mentioned. And in a sense, we're going to see that this principal quantum number is going to be vital for us in trying to describe various aspects of the shapes of orbitals. And in case we come across a specific discrimination, perhaps using this particular number, then therefore we're going to see that this is a description for energy, angular momentum, or specific shares and other forms which we are going to come across. Now, in our next discussion, we're going to look at another quantum number, and that together with this one is going to form a range for us in trying to understand the various quantum numbers that we're going to come across in trying to represent the shapes of various orbitals. So that is it for now, guys. By God bless you. Catch us in our next video.